Look at the problem on the pinhole camera. An object 50 cm tall is placed 1 meter in front of the pinhole camera with length 20 cm. A say what is the height of the image and the magnification produced. B say if the object distance is double, what is the size of the image produced? How is the magnification affected? Now, this problem has to do with light. You have to understand that there are two methods in solving a problem. You can use a geometric method, you can use the method of calculations. The geometric method is where we use the rectilinear propagation of light principle. A light travel in a straight line using these dash rays. So you see here from this method, this is a pinhole camera and this is a pinhole, a very tiny opening at the camera. We have the screen here on which the image is cast. Now, the length of this camera is 20 cm. So that means the image distance is 20 cm. This is the object, some 50 cm high. We also have it placed 1 meter away from the pinhole. Now, from the principle of rectilinear propagation of light, you understand that if this ray leaves the hairs of this image, this object, and it moves in a straight line, it enters the pinhole at this point, it goes down. Similarly, a ray leaving from the tail of this object will reach up. So you see, that's how we say the image formed by a pinhole camera is an inverted image. That is, the image is upside down. The head of the image is pointing downward. Now, if you use geometry, that is, you use your ruler to calculate the exact length of this material with a 50 cm, and then you take 1 meter away from this particular pinhole, you observe that once you follow the propagation, rectilinear propagation of light, the image form here will be the desirable height that we are interested in. If you take your ruler and measure them, that's one way. Without using any calculation, without using any pen, text in your ruler, draw your diagram, you understand a light travel in a straight path, you will be able to find the image height of the image. You will also be able to find the magnification of the image. Magnification is the image height over the object's height. Good. Now, in method 2 is what we're using the analytical method or the calculation method. The data that we have, firstly, we have the object height to be 0.5 meter. We have the object distance to be 1.0 meter. We are converting the centimeter to meter. You have the image distance to be 0.2 meter. You have image height to be question mark, the answer for the height of the image, and also want to find the magnification of that image. That is for the A portion. Now, you must understand or remember the magnification formula. We say that magnification M is equal to HR over HO, which will be equal to dr over do. So if I have HO, DO, dr, I can find HR by taking these two. I can use these two, this portion right here, to be able to find my image height. So that means HR over HO is equal to dr over do. Obviously, making HR the subject, HR is equal to dr over do multiplied by HO. And we substitute a value. Dr is 0.2 meter, do is 1.0 meter, HO is 0.5 meter. You now have meter cancel meter. You have 0.2 or 1 is 0.2. 0.2 multiplied by 0.5 will give you 1. HI is equal to 1.
0.2 times 0.5.
0.2 times 0.5.
0.1.
0.10 meter, which is 10 centimeter. So that means the image that will be formed on the screen, if we use the rectilinear propagation of large meter, you have 10 centimeter high image formed on the screen. Similarly, if you use a calculation method, you will derive at 10 centimeter. Now, they want to find the magnification. So once you have HR, we can use another formula. We can relate M to this, we get answer. We relate M to this, we get answer. So N is equal to dr over d over. Dr is what? Dr 0.2 meter. Do is 1.0 meter. That will be equal to 0.2. So the magnification of this particular object is 0.2. What that means? That means the object is demagnified, right? When you have a magnification greater than 1, it means the object is magnified. That is, the object is larger than the image is larger than the object. But then when you have a magnification less than 1, it means that the object is demagnified. The image is smaller than the object, which is exactly shown in our diagram. The image from here is smaller in height as compared to the object of that image. Is that clear? Alright. Now, we move to the B portion. The B portion says, if the object distance is double, what is the size of the image produced? So you also want to find, using the same formula here, this is the image height. We have to find the image height divided by DO is double. So HR is equal to DR still remain constant. That is the image distance still remain constant. The other distance DO is double now, multiplied by the object height. 50 centimeters, 0.1, 0.5 meter is still constant. So this will give you, now when the object distance is double, the object distance first of all 1 meter, when you double become what? 2 meter, right? Good. So you now have dr to be equal to 0.2 meter, do is 2.0 meter multiplied by ho will be what? H is constant, out of the image 0.5 meter. So h will be equal to what? 0.2 divided by 2.0 multiplied by 0.5. What we get?
0.05.
You get 0.05 meter, which will be equal to 5 centimeter, right? Good. So what happened? The object height remains the same, but we get farther away. We expect the ray to converge closer as we move farther away from the pinhole. That's the reason why the image gets smaller as the object moves farther away, even though the height is constant. Good. Now, the next thing say, how is the magnification affected? Now, magnification and magnification M is equal to HR over HO. Now, HO is constant, but HR has changed, right? So it now becomes 0.05 meter over HO is 0.5 meter. M is equal to what?
0.1.
0.1 meter, which is, sorry, 0.1, just 0.1. So now what happened? Firstly, when it was at 1 meter, the magnification was 0.2. When it go further apart at 2 meter, magnification is 0.1. What happened? The object get more smaller in size. I mean, it demagnified. Okay, thank you very much, and we'll solve no problem on this.